Good morning, dear students. Welcome to another session of microwave and antennas. So, in a previous session, we discussed regarding what are the fields which are pertaining to the dipole. So, in which we discussed first what is meant by a dipole and what is a short dipole. So, if the length of the dipole is very much lesser than lambda by 10, then we classify that dipole as a short dipole, or else it is not classified as a short dipole. That is, we considered the length of the dipole should be less than lambda by 10. If this is the case, then we call the dipole as a short dipole. So then we looked into what are the field parameters which are associated with the short dipole. So that is, this is the short dipole what we have considered. So by considering a small elemental length of this dipole, we estimated what is the field at a point P. At a point P, and based on some assumptions, we were able to estimate what is the near field parameters which are present at point P. So which is at a distance of R from the origin of the system what we are considering. So these were the parameters what we had discussed. So in the end, we obtain the near field equations, which is ER, E theta, and H phi components for the short dipole. And for far field, what we did, we eliminated the terms 1 by r square. And for the far field, what we had done, we eliminated the terms 1 by r square and 1 by r cube. That is, we assume that they equate to nearly equal to 0. So only 1 by r parameters are retained, and we observed that in the far field, we have only two components, that is E theta and H phi component, and the field equations pertaining to that will be containing only these elements. These will be equated to 0. Similarly, this one will be equated to 0, only this parameter remains. So these field values are required for estimating few other aspects. So this is what we had discussed in the previous session. So now let us see what is the radiation resistance of the short dipole what we have considered. So here we can see the derivation pertaining to the radiation resistance of the short electric dipole, or sometimes it is called as the Hertzian dipole. And since it is a short dipole, we get to know that the length of the dipole will be less than lambda by 10. So this is the equivalent representation of the dipole what we had seen in the presentation over here. So this is the dipole. Its equivalent can be represented as a wire which is of length L, and along with which the current I is flowing, and we have the charges at the opposite end of the wire. So keeping this as the assumption, or this as the concept, let us look forward how do we obtain the radiation resistance. Now when we want to obtain radiation resistance of a dipole, we have to refer to two things. First, we should know what is the pointing vector, which is nothing but the S parameter, which is the power density, that is power flow per unit, power flow per unit area. It is a power flow per unit area. But when we're considering pointing vector, what we need to consider is we need to consider the average value of this parameter. Yes. So here we need to consider the pointing vector or the parameter S, or it is called as the power density, power flow per unit area. Then apart from that, we make use of another parameter, that is power radiated by the antenna, which is given by I square into R, where this R parameter is nothing but the radiation resistance which is associated with the antenna. And this I is relevant to the RMS value of the current which is flowing through this wired or this short dipole. So these are the two things what we have to consider when we are obtaining the radiation resistance of a dipole. So now let us see what is the average Poynting vector will be. Now we have the average Poynting vector which is given by this equation, which is half of real part of the cross product of E and H, its complex conjugate. Its complex conjugate over here, that is H star. Star indicates that it is the complex conjugate of that parameter. So this is what we will be considering. So now, since we are interested in radiation resistance, we generally prefer the far field parameters. So in the far field, how the antenna is actually observing, how say another antenna is observing this dipole. So that is what your radiation resistance gives. So when that is the case, what happens is this parameter which is there, E cross H star, will be uh, equated to its parameter, wherein we know that in the far field we have only the E theta component, and in the far field for H we have only the phi component, H phi component, based on the geometric consideration what we have seen in the previous session. So the electric and magnetic fields which are present are nothing but E theta and H phi. So now when I simplify this parameter, right, what we have is, if I take the cross product, I have E cross H, which is given by magnitude of E into magnitude of H into sine theta. And in order to identify the direction, we consider a unit vector in the direction normal to both the directions of E and H. Now, since E is having only E theta and H is having only H phi component, what this equation we can write is, we can consider this as magnitude of E theta into magnitude of H phi. And what is the theta? That is the angle between electric and magnetic field. The angle between the electric and magnetic field is always 90 degrees. That is, they are perpendicular to each other, electric and magnetic field. So therefore, what happens? The sine theta equates to 1. That is, sine 90 is equal to 1, and this one gives you the direction of the normal. So therefore, what we have is, sorry, I forgot to put the star. So it will be, that equation will be equated to H star sine theta. I'll not consider the direction at present. So it will be magnitude of E theta into magnitude of H phi star. H phi star. So this is the equation what we will be having at the end when we simplify the average Poynting vector. Now, what happens is, if you just observe the field parameters over here, if I observe the field parameters here, you can see this, all these components here, I'm not having any complex parameter. I need to estimate what is the magnitude of this E theta and magnitude of this H phi. Now, why we are considering only E theta and H phi? Because we are considering the condition of far field. We are considering far field components. So in far field, this is 0, E phi is 0, HR and H theta is 0. Only E theta and H phi components are present. So now we need to equate, we need to find the magnitude of this parameter. But in far field, these are equated to 0. So only parameters which we have is this one. So we need to identify what is the magnitude of this entire parameter what we are observing. So if we try to identify the magnitude, what we'll be having, if you just observe, we will be having I naught into L. It's this magnitude will be given by based on the theta value e raised to j omega t, and magnitude of e raised to jx is actually equal to 1. So therefore magnitude of this one will be 1, then divided by this parameter which is 4 pi epsilon naught. And here you can see that it is a j parameter which is present, j omega by c square r. So in this case what happens is you get omega divided by c square into r. Now how it is equal to this one is, if you remember, if you have a plus jb, that is a complex number, and if I want magnitude of this, so what is the equation? We obtain it as square root of a square plus b square. So in this case, if you just observe what we are having, we don't have the real part because here we have j parameter, we don't have the real part. So real part is 0 plus we have the imaginary part for this equation. So if I obtain the magnitude of this, what we have square root of 0 square plus b square, which is nothing but b. So this b is nothing but the imaginary part which is present over here. That is its magnitude associated with this. So here except j, you when you consider all these parameters, you will obtain the magnitude of e theta. And this magnitude, right, what we do is we obtain magnitude of e raised to jx, which is equal to 1. So if you want, again you can go ahead and see what is e raised to jx. It is cos x plus j sin x. If you remember, cos x plus j sin x, this is nothing but e raised to jx parameter. And when we take magnitude of e raised to jx, when we take magnitude of e raised to jx, it is nothing but you're taking magnitude of cos x plus j sin x. Okay, so this is nothing but square root of cos square x plus sine square x. What is cos square x plus sine square x? It is equal to 1. So this value will be equal to 1. Therefore, magnitude of e raised to jx or e raised to j theta is equal to 1. So that therefore this one turns out to be 1. So in the similar way, we can obtain the magnitude of this parameter. So in this case, we have to consider the far field component. So this one equates to 0. We need to consider only this parameter. So as it has only the imaginary part, what happens is magnitude of this one will be equal to I naught L sine theta divided by 4 pi into omega by CR. And in some books, what they do is they replace omega by C with beta. Omega by C with beta. So therefore, what this equation turns out to be, sometimes we write it as I naught L sine theta divided by 4 pi, that is for this condition, into beta divided by r. So sometimes they write it even in this form. So what we are having, e theta and h phi. So next what we do is, once we have simplified this equation, what we are having is this cross product will be simplified in this form. Now we know what is magnitude of h and what is magnitude of h phi star. So since there is a complex conjugate, just the sign changes over there. When you take the magnitude, again it remains the same. So now what we have, therefore the radial component of power density is equal to half of real part of E theta and H phi star, that is magnitude associated with this. Now what we do is, instead of considering both the parameters together, we can consider equate E theta and or see what is SR, or we can consider H5 and see what is SR. So how do we do that? We make use of this equation. We make use of this equation. Remember, this is still in magnitude. Magnitude of E theta into magnitude of H5, its complex. So now we know that E theta by H5 is nothing but the intrinsic impedance of the medium which is under consideration, which is given by square root of mu by epsilon, where mu is the permeability and epsilon is the permittivity of the medium what you have considered. So now if I can represent this with eta, or sometimes it is represented with Z. So therefore what happens is E theta is equal to H5 into Z. I can replace this with this equation. So E theta is equal to H5 into Z. What is Z? It is square root of mu by epsilon. Now what we do is we substitute E theta in this equation. So therefore what we'll be having is, we'll be having actually magnitude of H5 into Z, this thing, into magnitude of H5, its complex. So now we have magnitude of H5 into magnitude of H5, its complex, is actually equal to magnitude of H5, its square. Magnitude of H5 in its square. So therefore this parameter will be simplified to magnitude of H5 its square into the intrinsic impedance. So this is this is the parameter which is associated with the power density or the Poynting vector. Now, when we still further simplify this, if we consider only the real part from the equation, you could make out that when we consider the real part of the magnitude, we end up with the power density equation, which is equal to half into magnitude of H5 square into Z, where Z is given by what? Square root of mu by epsilon. Square root of mu by epsilon. So this is the radial, this is the power density in the radial direction. Now next what we have to do is, once we have obtained the power density using power theorem, I can obtain the total power which will be radiated by the dipole which is under consideration. So by power theorem, what we have, power theorem states that if I want to identify what is the total power, then I have to take the surface integral. I have to take the surface integral of the power density what you are considering. So it will be double integration of the power density, average power Poynting vector or the power density into with respect to ds, where ds is what? Ds is, again from the previous sessions, it is r square sine theta d theta d phi. It is this parameter. Okay, so this is the power theorem relation. So now what we do is, we have seen that SR is given by equation 5. So now what we do is we substitute equation 5 in this equation and we simplify that integration parameter. In this again we substitute H5. What is the magnitude of H5? So in previous case we observed that what is the magnitude of H5 from the equation what we had considered. So from that I'll directly refer to the final equation what we have obtained based on the derivation. So here you can observe that we have the same equation, which is I naught into L sine theta e raised to j parameter equates to 1. So therefore that parameter is gone off. Then we had omega by c. We had omega by c, which is nothing but beta. So that parameter is coming over here. We had omega by cr. So that is beta by r. So this parameter, we have it over here. So from this case, you can see that we have I naught L sine theta. This is 1. So we consider only this one. So it will be omega by C by R, C into R, which is beta by R into 4 pi. So the same equation, when we simplify it, we have H phi, which is given by this equation. So now magnitude, this is the magnitude, and for square, you square this term. You square this term. So now what you do is you substitute H phi, you substitute H phi in this equation. In this equation, so which is actually present in the integration part. So when we substitute it in the integration and when we simplify this, what we end up is, when we simplify the overall parameter, we get the total power which is being radiated by the short dipole as square root of mu by epsilon, which is nothing but the intrinsic impedance into beta square I naught square L square divided by 12 pi. So this is the parameter what we will be getting for the total power which is being radiated. Now, next, what we need to consider is we need to consider the power radiated in terms of radiation resistance. So previously we considered what? We considered the power density and then we obtained the total power. Now, in the similar way, if we know the radiation resistance, then we'll also be able to obtain what is the total power radiated by the antenna which is under consideration. So for this case, what we have to do is we have to consider P is equal to I square into RR, where this I is nothing but the RMS value of the current which is flowing through the dipole, and RR is the radiation resistance of the antenna which is, or the dipole which we are considering. Now RMS value of the current, if I know the peak value, it will be given by I naught divided by square root of 2, where I naught is the peak value of the current flowing through the dipole. That is, here we are considering the dipole. I is the RMS value of the current, and if this one is having a peak value of I naught, then this I will be given by I naught divided by square root of 2. So that is what we will be having in this case. So I is equal to I naught divided by square root of 2. So when I substitute this equation over here, what I'll be having is P is equal to I naught square divided by 2 into RR. So now what we have obtained is we have obtained two equations for the power radiated, one in terms of radiation resistance and another in terms of, with the help of the field equation, with the help of the field equations. Now these two are will be equated, that is the two equations will be equated and simplified. So this is the equation for the total power what we have obtained due to the H phi or the field component, and this one is the field due to considering the radiation resistance. Now both are equated and simplified. When you simplify, what you get is radiation resistance, which is given as square root of mu divided by epsilon into beta square into H square divided by 6 pi. Now if we assume that the uh, the space what we are considering is vacuum, then what happens is this is nothing but the intrinsic impedance, that is Z, or sometimes denoted as eta. So this will be equal to square root of mu naught by epsilon naught, which will be equal to 120 pi ohm, or sometimes it is represented as 377 ohm. So for present derivation, I'll be considering 120 pi ohms. So now when I substitute 120 pi ohm over here, that is for this parameter, and if I simplify it, what I'll be obtaining. So here we consider mu by square root of mu by epsilon as 120 pi. It is beta square into L square divided by 6 pi. So which will end up in 20 times beta square into L square. But what is beta? Beta is 2 pi by lambda. So when we substitute beta in this equation, what we'll be having? We will be having 20 into 2 pi by lambda h square into L square. And when we simplify, this is the final equation what we will be obtaining. That is, radiation resistance for the short dipole or the Hertzian dipole is 80 into pi square into L by lambda its square. Now, you might have observed in some of the cases, instead of writing it as L lambda, sometimes it is represented as L with a subscript lambda. In a few other cases also, you might have seen we had written C lambda, which is nothing but C divided by lambda in this antenna terms. So here, this is the final equation for the radiation resistance of the short dipole. So this I can replace it by L with the subscript lambda. This is nothing but L by lambda its square. So this is the representation. And if you still simplify this, you will be having 790 into L by lambda its square. So this is the derivation pertaining to radiation resistance of the short dipole. So this is for the radiation resistance of the short dipole or the Hertzian dipole. So now let us go for the next aspect, that is the fields which are associated with the lambda by 2 dipole. So previously what we saw that if the length of the dipole is less than lambda by 10, then we classify it as a short dipole, and the fields what we had obtained, so these fields, that is the near field and the far fields, associated far fields, will be applied to that short dipole. Now what if the length is greater than lambda by 10, greater than lambda by 10, and another parameter what we consider is if diameter is less than lambda by 100. So if this is the case, so generally this is the case for thin linear antenna. That is, if the diameter of the wire what you're considering is less than lambda by 100, we classify that as the thin linear antenna. So now in next this thing, we look for what are the fields which are associated with the thin linear antenna. So here we consider a dipole or the wire which is of the length L, and we assume that this dipole is placed along the z axis in such a way that origin of this axis or the center of the z axis forms the center of this dipole which is under consideration. So therefore indirectly the length of this one is L by 2, and the length of from here to here is L by 2. So these are the two length parameters associated with this. So in the positive z axis, you have a length of L by 2, and in the negative z axis, you have a length of L by 2. So when I specify, it will be like plus L by 2 over here with respect to z axis and minus L by 2 over here with respect to the negative z axis. Now again, what we do is we consider an observation point to identify the total field which is presented due to this dipole which is under consideration. Now here when we consider this, what we do is if we have a dipole which is not short, so it is not a short dipole, so it is not satisfying the condition, that is L less than 10. So this condition is not satisfied. So in this case what is done is you assume one thing. Now, if I have to identify the total field because of this dipole, what we do is we can make an assumption that the small parts of this antenna of this dipole, I can consider this as a short dipole. I can consider this as a short dipole. So this entire antenna is considered to be a combination of multiple short dipoles, multiple short dipoles. And what we do is we estimate the field because of this short dipole. So because of this short dipole, I'll be having a field. So because of this short dipole, I'll be having a field. So now what I do is I take the vector addition of all these fields due to this short dipole. And when I take the vector addition of these, I'll be getting the overall field, which is due to the non-short dipole, which we are considering. Say the thin linear antenna, what we are considering. So based on that, we can identify the overall field which is due to the thin linear antenna. So one thing what we have to note down is this thin linear antenna is assumed to be made up of small chunks of short dipole. And what is the field due to this short dipole can be identified, and already we have identified what is the field due to the dipole. We have already identified that, but now small changes we have to incorporate, and then we have to look forward for what is the total field. Now here you can just observe what they are doing is they are considering a small elemental length of dz, and this is at a distance s from the observation point. And what is the field due to this element has to be identified. When you have to identify this parameter, right, you need to know at what distance it is, what is the current flowing through that, and at what distance this small elemental parameter is, or the small elemental antenna what we are considering over here. So when we consider that, again we need to consider the retarded current. So as we had discussed in a previous session, right, we had I is equal to I naught e raised to j omega t. So which is the current which is flowing through the conductor. But in because of the radiation, say property, what happens is the field is distributed or because of the disturbances. So that disturbances is observed because of the retarded charge or the retarded current. So that is retarded current is given by I into e raised to j omega t minus r by c. So this is the time taken by the wave to travel towards the distant point. So that gives you that gives rise to the retarded current. So here we had only r by c what we had considered. But now we have to consider few other parameters when we are considering the thin linear antenna. So when we're considering this, the retarded current is given with I naught into sine. This is nothing but beta, which is 2 pi by lambda. It is beta into the length, beta into the length into the retarding parameter, the retarding parameter. So when we consider the dz, so it might be this side, it might be this side. So when we consider this parameter, you can just observe what is the length of associated with this is L by 2. This is L by 2. If I subtract minus, if I subtract z from this, if I subtract z from this, I'll be getting this parameter. So what is the field? What is the current flowing in this element? That is what we'll be getting in this equation. So here we are taking L by 2 minus Z, which will give me this parameter. So that is what is specified over here. So it is 2 pi by lambda into L by 2, either plus or minus. If it is in the other direction, it will be L by 2 plus Z. So here it will be L by 2 minus Z. So if you're in the positive Z direction, it will be minus Z. If you're in the negative Z direction, it will be plus Z. So now here we can just consider the retarded current is I naught into sine 2 pi by lambda into L by 2 plus minus Z into e raised to j omega t minus r by c. So here this parameter, what is there? So previously we had only this case, only this one. But this parameter is included because it gives you the form factor of the current which is flowing through the antenna. Now, because depending on the length, right, the distribution of the current also varies. It might be when I observe the field, it might be like this for the lambda by 2. When I still go for say lambda by 4, the distribution will be like this. If I still reduce, the distribution might be like this. So that is, I might have the distribution which is present like this. So these are just a few things to note down in this case. So this parameter is nothing but the form factor of the current which is flowing in the antenna. Now, based on these aspects, right, we have for this elemental parameter dz over here, we have we have the field parameter. This is the elemental field E theta, which is given by J times 60 pi into I, the retarded current, into sine theta dz divided by S into lambda. And similarly, we have the magnetic field, the elemental magnetic field due to this elemental length dz, which is J into the retarded current sine theta dz divided by 2 times S lambda. So these are the fields which are associated with the small elemental parameter. Now, if I want to obtain what is the field due to this entire, what I do is I integrate these two equations. So if I integrate, I'll be getting E theta for the thin linear antenna and H phi for the thin linear antenna. So based on the integration, what we have the field parameter, which is given over here, which is H phi and E theta. So where we have minus j I naught divided by 2 pi r into cos of beta L cos theta divided by 2 minus beta L minus cos of beta L by 2 divided by sine theta. And E theta is what? E theta is 120 into H pi. So when you multiply that, what happens is we obtain 60 into I naught R into this parameter, where I naught is identified as what? I naught into e raised to j omega t minus r by c. So that is what you are just representing. So it is the retarded magnitude of the current what you are considering. So this is the field which is associated with the thin linear antenna. So if I want the derivation, right, you can just go through the derivation. So here we can see that how the distribution is actually happening, the distribution of the field what we are considering, or the current what we are considering. How is this current distributed? So if it is lambda by 2, the current distribution, when we measure the current, right, it will be in this form. So peak will be at the center and zeros will be at the end. So if it is 3 lambda by 4, I'll be having two peak values, one at this point and one at this point. So this is how it goes around. If it is lambda, I'll be having 0. I'll be having a 0 value of or the current over at this end, at the middle, and at the other end. I'll be having two peaks at these 2 points. So here you can see that it has changed its direction. So previously current was flowing like this, but when it becomes 5 lambda by 4, the direction of current changes, because of which the magnitude what we are representing changes. So it is just an indication that direction has changed. So this is the current distribution what we can observe when the length of the dipole changes. So if you want to go through the derivation, this is the derivation which is pertaining to that. So in which we start off with the instantaneous current, and then we continue with its representation on what are the parameters. When do we consider L by 2 plus Z, and when do we consider L by 2 minus Z? So all these things we can see over here. So we have this parameter over here represented, and this is the far field equation which we had obtained for short dipole, E theta for the short dipole. So from this itself we continue. From this itself we continue. So we make some simplifications based on the observations. Once we observe that, we will be able to simplify one of the parameters to 60 pi divided by lambda, and we obtain E theta. Now this E theta is nothing but the elemental parameter which is due to the elemental condition. And in this case, R what you are considering is nothing but the distance S. That is this one. So you are considering this parameter, this distance S, you are replacing over here. So this is just a sample what I'm showing over here. So in the similar way, you can identify for H5, simplify the parameter and obtain what is H5. So from that, you substitute in the integration and simplify it. So when you simplify this equation, you will be ending up with the final equations. So wherein we have obtained what? We have obtained H5 and we have obtained E theta. So these are the final equations what we have observed. Okay. So next, let us have a look at one of the problems related to radiation resistance. So now here we have a thin dipole whose length is lambda by 10. If its loss resistance is 2.5 ohm, find the radiation resistance and the efficiency of the antenna what you are considering. So when you're dealing with this, generally first consideration is you can observe that the length is lambda by 10. We need to first identify whether it is a short dipole or not. Now, when you consider a short dipole, right, its radiation resistance will always be given by 80 pi square L by lambda square. But if it is not a short dipole, I cannot apply this equation. If this is not there, then I cannot directly use this equation because radiation resistance of those antennas are different. For example, if I consider the radiation resistance for lambda by 2 dipole, the radiation resistance of lambda by 2 dipole is around 73 ohms. It is around 73 ohms. Radiation resistance of lambda by 4 dipole is around 36.5 ohm. They are not linearly related with the length. Only in these cases we are getting it. For lambda it is different. For lambda it is different. It is not twice that of 73. We have to estimate it. Okay. So it is not straightforward. But remember, if they give you lambda by 2 dipole, so for lambda by 2 dipole, the radiation resistance, you can remember this values. Radiation resistance is 73 ohm, and for lambda by 4 dipole, the radiation resistance is 36.5 ohm. So these two values you can remember. So here what they are asking is, they are asking you to find the radiation resistance and the efficiency. You got to know what is the length. Now, based on the length, you can make out that length is lesser equal to lambda by 10. So it is on the boundary condition. So now here what we do is we consider this as a short dipole. We consider it as a short dipole. So if it is a short dipole, radiation resistance is obtained by this equation, which is 80 pi square into L by lambda its square. So therefore substitute what is L in this parameter. Here you can observe, and when you simplify, the radiation resistance of the antenna is obtained as 7.89 ohm. Now that is the radiation resistance what you have obtained. Now for obtaining the efficiency, we require two parameters. One is radiation resistance and one is the loss resistance. So these two things are required to identify the efficiency of the antenna. And the equation for efficiency is given by this parameter, that is RR divided by sum of radiation resistance plus the loss resistance. So when we simplify this, in this already the loss resistance is given as 2.5 5 ohm. So when I solve this problem, when I solve this equation, I'll be having a efficiency which is given over here, which is 75.93%. So for the given length, the antenna is having a efficiency of 75.93%. So this is with respect to the problems what we have discussed. Now there are few more problems what we can look out for in association with these aspects. So based on these field equations what we have discussed, right, we can have problems pertaining to these parameters with respect to the problem which is associated with radiation resistance and efficiency. So this is all for today's session. In next session, we'll be starting off with the discussion pertaining to what are the different types of antennas. Okay, thank you.